Hi everyone, thanks for coming. My name is Kevin Scaldeferri. I'm a principal software engineer and architect at New Relic, and I'd like to tell you a bit about the distributed database system that I've been working on there for a number of years with a large team of other people as well involved. We have lawyers, and you can read this if you care later. So outline of what we're going to do, I'm going to just kind of introduce the distributed database and what it is. We'll spend most of our time talking about how it has evolved over time. So this is a system that's about 10 years old at this point. Some of the lessons that we've learned along the way, and then just a little bit about kind of some of our future directions that we're planning on. So what is NRDB? Literally, it stands for the New Relic database, not a super original name. But if I had to kind of summarize in one sentence how to describe it, it is a massively multi-tenant, globally distributed, mostly immutable time series database for schemaless telemetry data. So this is where we store all of the observability data that our customers send us that they're interested in storing and querying to understand their systems later. Internally, the code name for this system when it was started was Dirac, and if I accidentally say that instead of NRDB, that's we're talking about, and also that image will show up on a slide or two later. So the overall sort of conceptual design of the database looks like this. So it's composed of an insert tier, so data comes into insert workers. It's written into files on disk, put into a storage layer. Queries come in, they go into a query routing system, which farms out parts of the work out to a very large tier of query workers that all do part of the computation, and then it all gets merged together. The live edge of data, which is residing on the insert workers, it's being written currently, also gets queried by the routers as well. So this is, if you've been to any past talks at this conference or others by Druid or by Honeycomb, or this is kind of a fairly similar picture. All of us read the Dremel paper, took some ideas from that, and kind of implemented a system that looked, similar in the large scale. Some of the design goals that are specific to our choices when we were building this. One was ease of use. So because we're a SaaS company and we want customers to be able to onboard very quickly, we want to make it really, really easy for them to start sending us data. So to support that, we don't require people to predefine any schemas for their data. We don't require them to define any indices. For that matter, we actually don't even require people to predefine tables that they're going to start sending us. So at any time, someone can decide they want to start tracking a new piece of data and send it to us, and we just start storing it automatically. We want the system to be very scalable and very high performance. So sub-second time to glass when data shows up, time from when data is sent from a customer to when they're able to view it in queries. Queries are very fast. Median is about a 50 millisecond response time. And for the power users, we have a very expressive SQL-inspired query language that you can use. And then sort of the last big design principle is we want people to be able to query all of their data in one place. So if you're sending us different types of telemetry, if you're sending us logs and traces and metrics, we don't want you to have to go to 3 different places to look at that. We want one place where you can look at all of that data together. You can run queries which correlate that data through a single interface. Similarly, if you have lots of teams who are using the system, lots of different applications, you want to be able to tie those things together in one place as well. We don't want to wall off segments of your data. Okay, so that's the kind of real quick, big picture of the product. And now we're going to spend kind of most of the time talking about what the architecture of the system looks like and how it has changed over the last 10 years. So just to kind of tease where we're going, I joined the team in 2014. At that time, we had a single Dirac cluster that ran in our data center in the Chicago area. It was I guess for the time, what felt like a pretty big system. It was, we had hundreds of JVMs in the cluster, thousands of CPU cores, hundreds of terabytes of data that we were storing in there. But today, the system is much, much bigger than that. So it's globally distributed. There are clusters that are all over the world in multiple cloud providers. There's tens of thousands of JVM instances involved. And we talk about exabytes of data in the system currently. But what's sort of interesting is, as far as our customers are concerned, like, nothing has actually changed. They don't have to know about all of those different clusters and all of those different places. They still go to all of the same UIs and APIs that they used to continue querying their data, even though it's much more complicated under the hood now. So this is sort of a picture of the very first version of the architecture, how it started 8-9 years ago. So at this time, as I said, we were running in our own data centers. Docker had not yet actually been released yet. So we were running JVMs directly on a big pile of dedicated hardware for this system. We had lots of SSDs crammed into the chassis of these Dell servers. Disks were very expensive. That was actually about 60 or 70% of the cost of the system, was all of that local storage. Made somewhat more expensive by the fact that we're storing all of the data redundantly. So we use sort of a React-style consistent hash ring strategy to store multiple copies of the data and be able to handle failures and still have all of the data available. We did have a backup of all of the data in S3, but latency was very high from our data center to AWS, and costs were very high to actually download data. So that was really more of a disaster recovery strategy, not actually part of the operations of the system at that time. And then the last thing of note was that, so what looks a little bit different here from the conceptual architecture is that data ingest was actually coming in the same front door that queries were coming in. So data ingest came in through an HTTP API into the query routers and then got sent off to the insert workers from there. And this was a major pain point for the system early on, because what that meant is that if we got a huge burst of query load, we might exhaust all of the server threads in the routing tier, and now we start rejecting data payloads. And rejecting data payloads means that we are losing customers' data, and that makes customers really upset. So we needed to solve that problem. And very early on, we did that by introducing Kafka. So we were fairly early on the Kafka adoption curve. This was it's probably version 0.7 when we first started using Kafka. But we switched our ingest so that it was coming in through Kafka topics, consumed directly by the insert workers, and outside of the query path. We also made another small change to actually decouple the processes that were doing that live edge querying from the ones that were writing the files. So we created these sort of sidecar processes called live query workers, which just sat on the same physical hardware as the insert workers, but they're separate processes. They have different CPU and memory allocations. They have different GC profiles and tuning and what have you. And that allowed us to keep those two workloads from interfering with one another. So sort of 2014 to 2015, we evolved into an architecture that looks like this. There's a detail about this, which I'm going to kind of go into in some detail right now that'll seem a little bit in the weeds, but we're going to come back to it later in the talk, which is, so we added in Kafka, and one of the things you have to decide when you're using Kafka is how you're going to partition the data coming into that topic. The default, if you don't do anything else, is you're going to get random partitioning. This would have worked for our system, but it would have been really inefficient. So we're storing data in a columnar file format, and a lot of the efficiencies of columnar file formats comes from having large runs of similar data being stored in the same place. If instead every payload was getting sprayed to a random insert worker, our column storage would be very inefficient. We wouldn't get any of those gains. A more subtle problem is that it also creates a very large failure domain. So now if every customer is getting sprayed out to every insert worker, if one of them fails, we have impacted all of our customers rather than just a subset. So that's not ideal. Usually the next thing you would do with Kafka partitioning is to pick some key, say a customer ID or a particular data stream. You do a hash and you mod. And for a lot of workloads, that's perfectly fine. You'll get a nice even distribution. We have a very dramatic power law distribution in the various data streams that we're ingesting. And it turns out that you can get unlucky there and you can land 2, maybe even 3 really big work streams on a single partition. And now things are all sorts of out of whack. So we came up with a sort of, our workaround for that is that we look at sort of the largest 1,000 or so workloads, data streams, and we run a bin packing algorithm over those. So we make sure that that's all evenly distributed across partitions. And then everything else we can go to the hash-based distribution. And this is actually sort of a real-time feedback loop that's going on. So we're constantly watching what the workloads are that are being ingested and redistributing things as necessary to keep an even workload across all of these workers. And that's sort of important because, as I said, like at any moment, a new customer can show up or a customer can start sending us a new workload that we've never seen before, and we need to be able to adapt to that relatively quickly. The flip side of this is the query routing side. So as this ingest is moving around, we still need to be able to query that live edge of data wherever it happens to be. And your first, like the naive instinct here is to base that on, look at the insert routing rules and route queries to the live edge based on that. That actually doesn't work out in practice. It's subject to a variety of race conditions and other complications. So in fact, what we realized we needed to do was actually like rely on our metadata store. So every time insert workers see a new data stream that gets registered in the metadata store, query routing uses the metadata only in order to route queries. So this gives us a picture that looks like this. So we've added this ingest routing logic on the front end. Queries are still coming into the routers. They're only using metadata to decide how to execute a query. And for a few years, this is kind of what the architecture was. Nothing changed very much. We did adopt Docker somewhere in the middle of that time period. But what was going on meanwhile was that we were experiencing exponential growth. So we're getting more customers in. Customers are sending us more and more data. Those query worker clusters are getting, or that query worker cluster is getting bigger and bigger. The ingest tier is getting bigger and bigger. Our Kafka installation is getting bigger and bigger to a point where, at least by some measurement, at one point we were actually running apparently the largest Kafka broker cluster in the world. Yay, we won. And then Gwen asked, out of curiosity, why did you decide to cellularize? Is there a blog or talk on the architecture change? And well, I'm glad that you asked. So it turns out that yay, we were winners, but this is not actually a great situation to be in. You brag on Twitter or on stage at conference talks, but meanwhile, your ops teams are really not having a good time. When you are running the largest cluster of whether it's Kafka or Cassandra, MySQL, anything, you're going to be discovering new failure modes, new scaling bottlenecks that no one else has run into, and you're going to have to solve them pretty much without any help from the rest of the community. This is, I don't know, sometimes it's fun, but most of the time it's not fun. Particularly at like 2 in the morning, it's really not fun. So we kind of realized that this was not actually the situation that we wanted to be in. And in fact, 2019, it was not just Kafka. It was like most components of our infrastructure that we were building upon, we were running into serious scaling limits. Kafka, MySQL, Redis, Zookeeper, and we managed to find ways to push through those scaling limits at that time. But what we knew was that that growth curve was going to just keep on going up. And those solutions that we found weren't actually going to last very long, and that we needed to actually think about a different approach to how we were going to continue to scale NRDB and the company as a whole. So this is when we made a decision to embark on sort of a pair of coupled changes, but to migrate to a cell architecture approach for our deployments, and at the same time to migrate into public cloud. So the cell architecture just means that sort of rather than making a single cluster or single installation bigger and bigger and bigger, you kind of cap things at a certain size, and then you stamp out new copies or new cells in order to scale. So this is very much like we learned years ago that typically vertical scaling is kind of not the preferred approach for most services. You'd rather scale horizontally with more instances of the service. So this is sort of similar. We don't want to keep vertically scaling our clusters. We want to kind of pick a scale where we know that we can actually operate it, where we understand how the system behaves, and then keep things at that comfortable size and just make more copies of it. So this helps us for operations. It also helps us with limiting failure domains. So now, if a cell fails, instead of every customer being affected, it's a subset. Why the cloud? Well, basically, like that growth curve also applies to hardware management. We were getting really sick of managing our own hardware. We decided we would outsource that to someone else who specializes in it. And we also really wanted to get access to sort of the elasticity benefits of the cloud for a variety of reasons. So we got started, as most people do, with a lift and shift architecture. So kind of looked like this, right? We just took a whole bunch of copies of, I'm just showing kind of the NRDB picture here, but it was actually our sort of entire ingest processing pipelines, which sort of terminate at NRDB and the query layer there. So we put a bunch of copies of that in the cloud, and then we had to solve a couple of problems that required like thinking about what different people's kind of needs and wants were around this change. So we realized that most customers, almost all customers don't care about this. Why would they care? This is just a detail of how we run our systems. Some customers care about some things like compliance regimes. Are they in a FedRAMP certified cell or not? If we have a failure, they want to know, am I in one of the cells that's being affected by your current failure? And then we wanted to have kind of the freedom to be able to move customers around for various reasons. So we want to keep loads balanced across the cells. If there's a problem of one sort or another in a particular cell, we want to be able to shift load around to kind of avoid the failures. So we're faced with this question of, okay, how are we going to meet those needs of various people? We still have data that is coming in through the same ingest endpoints that customers have always used, and we have queries that are coming in through the same URLs that they've always used. We certainly don't want to tell customers that they have to start using new URLs that are like specific to one cell or another. That would be like really weirdly exposing our architecture to our customers. And on the ingest side, we were sort of thinking about like, okay, what are the properties that the system for distributing ingest across cells were? And what I actually realized was like, hey, we've seen this problem before. This is the same problem that we had with Kafka partitioning. And what we needed to do was apply sort of a similar approach where some of our really, really big customers, we want to make sure that we don't put two giant customers into the same cell. So we need to kind of bin pack a subset of our traffic. And then beyond that, we can do simple hash-based distributions. The implementation of this is totally different from the Kafka partitioning. The way it works is that we use Cloudflare workers out on the edge. These are little processes that run a JavaScript program. They talk to a service called Wayfinder that we run that does this bin packing and distribution, these routing rules, and then the Cloudflare workers, when they get in a request to the long-standing ingest endpoints, they know which cell to forward that onto. And then over on the query side, again, we'd learned the lesson, like, we don't want to be coupling query routing to those ingest rules. We actually need to have metadata about the real sort of ground truth of where data is. So we built this system we called smart query routing on top of a sort of higher level metadata store about where things are in cells. So we get a picture now that looks like this. So one of the things we did here was realize like we could reuse some of these solutions to problems which we'd seen before, but in this new kind of higher scale domain. Some other changes that kind of came along for the ride while we were doing this, we switched as an organization to deploying on Kubernetes. So when we had initially adopted Docker, we built a container fabric on Mesos and Marathon, which was great for the vast majority of stateless systems at the company, but actually like totally didn't help us at all for running a stateful system like NRDB. So when we switched over to Kubernetes, this was actually nice. We could now actually deploy all of our systems, including our stateful systems, with the same orchestration and have much more standardization across the company, even for these stateful systems. We still have to do some customization. We have some CRDs and a pile of operator code, but we have a much better structure for doing it. This also meant that we could switch our query tier to ephemeral instances and storage and just take advantage of Kubernetes orchestrating that. Ingest, we still need persistent volumes because that's like, at that point, the one and only copy of someone's data. But we can have ephemeral instances attached to persistent storage. The one thing that didn't work out was trying to use stateful sets. So like that seems like appealing for this problem. Unfortunately, there's a couple of reasons why that didn't actually work out for us in the end. But overall, Kubernetes was a big win for us in running a system like this. We also, now because we're in the cloud, we're actually much closer to S3, and transfer costs are non-existent. So we can now treat S3, S3 can be our primary storage, and we can treat local storage on the query workers as just a cache or performance optimization. So we massively reduced the amount of local storage that we had in the system, brought that down to 5% of the cost of the system, and we were able to do this with no impact to query performance up to the 99th percentile. The vast majority of queries that people are doing against observability systems like this are for the last hour or the last day of data, and so we keep that data set in the hot set, but at much lower cost. We did introduce a couple of problems, though. So one of these is to the fact that we had persistent user data in ephemeral cells. So for a variety of reasons, sometimes we want to be able to retire a cell and replace it with another one. In order to do this with the lift and shift architecture, we had to build this system where we copied all of the data from one cell to another, copied all the metadata also from one cell to another, and then built a transaction system in order to be able to do this without having any problems, any flaws in queries that we were running. And this is very time consuming and very complicated. It was a fun distributed systems problem to work on, but it added a lot of complexity into the system. We also had this problem, again, of the bin packing problem actually became harder because one of the problems is that customers actually vary wildly in terms of how much they query their data. Some people send us lots of data and actually never really query it. And some people query their data a whole lot. So there's like a 14 order of magnitude variation in this ratio against our customers. And trying to solve this bin packing problem is really, really difficult in the face of that. So we've got these two problems that we realized we needed to solve, and that it was time for us to say, okay, like the lift and shift has only gotten us so far. We need to actually think about what would the system have looked like if we had built it in the cloud from the start and with the cell architecture from the start. So that first problem, the persistent data in ephemeral cells problem, we realized we needed to decouple the storage there. We need to actually realize that our customers' data is not one of these commodity things that we want to be able to just replace and dispose of willy-nilly. Our customer data it's their collectibles. Like they really, really care about it. It's not interchangeable with any other data. It's not disposable. It's not replaceable if we lose it. So when we thought about that, we realized, like, okay, we need to treat the data very, very differently from the way that we're treating cells and containers and all of that. In fact, like, we knew how to do this. Like S3 was the one piece of our infrastructure that we had never really run into scaling limits with. So S3 is a great, durable place to store data. And what we needed to do was just go back to using it the way that S3 wants to be used. So instead of having storage tiers separately in every cell, we now have a centralized storage tier that can be shared across all of them, and now we don't have to move data around. That bin packing problem, the realization there was that this single multi-dimensional bin packing problem was really, really hard. But if we could turn it into multiple independent one-dimensional bin packing problems, those are easy. So much like we wanted to have different insert workers, numbers of insert workers, and different numbers of query workers back when we were in a single cluster, we want to have different numbers of ingest cells and query cells. So we pulled the query layer out of those lift and shift cells into their own cells that we can scale independently and that we can distribute workloads to independently of how the ingest workloads are coming in. Now we have a picture that looks like this, and we're actually like very much back to the original conceptual architecture, except that everything is like one level higher abstraction from what it used to be. So it's a sort of fun kind of fractal property to the system. The big takeaway here was that we could reuse these successful architectural patterns at higher levels of abstraction. And that was the approach that we needed to be taking with our cells instead of just with individual servers. I'm going to talk a little bit about multi-region. Again, this is one of these things, like most customers don't really care what region you're in, what cloud provider you're in. There are a few more reasons why some customers do legitimately care about where you're storing their data. And then we had some similar concerns around failure domains and other things. So the funny thing is, like, we'd actually gone multi-region before we went cellular or into the cloud. In 2017, we built an EU region, and at the time, we didn't have cells, we didn't have smart query routing, we didn't have this Wayfinder, what we thought at the time was that we wanted to actually just like really wall off the EU installation from the US in order to reassure customers about compliance concerns and data sovereignty. Unfortunately, what this also meant was that existing customers had no way to migrate from being homed in the US region into the EU region. And if you wanted to create new accounts that were homed in the EU region, you could no longer correlate your data that's in the US with that, or you couldn't see the history of your data that was in the US in the same place. You can go to the two different versions of the website, but you can't get that stuff all in one place, which had always been one of our goals in this system. So today, as we're building out more regions, we realized we need to take a different approach. We need to take the same approach that we were taking around the cellular architecture and just take it one more level higher and build ingest routing that takes into account those customers who have a strong preference about region or cloud provider. We can send them, route them according to that. Everyone else we distribute however we decide we want to. And then we have yet another third order metadata that allows us to route queries to the right region. Okay, so that's kind of where we are today. I'm just going to talk about, recap some of the lessons that we learned and advice. So first, being the biggest in the world of something is not actually a place that you want to be. It's a place that causes you lots of headaches. So cellular architecture, is a great approach for trying to cap the size of any given cluster, allow you to scale larger and larger without always being in the unknown. Look for ways to find scale invariant architecture patterns. So patterns of architecture which apply at multiple levels of scale or abstraction. If you can reuse things like that, it's often a benefit. Lift and shift. If you're starting on a cloud migration or a migration to the cellular architecture, it's a fine way to start. It's almost how you have to start if you're going to make any headway. But just keep in mind that it's not going to be the end state that you want to be in, and budget time to re-architect and pay off technical debt down the line. Again, by and large, customers don't care about your architecture. Try not to expose any of this stuff to them if you don't have to. You may have small numbers of customers who do have interest in this, but give people the option not to care. And then, finally, stateful systems are still hard. But if you're a company like us, state is what we're getting paid for. Customers send us state, expect us to store it and keep it safe for them and to query it. So, we'll keep solving those problems and having fun doing it. And just, a few thoughts about where we're going with this system, kind of future steps. So one thing that potentially has been bugging some of you is this line through the middle of the diagram. Because I've been talking about decoupling ingest and query, and if you look at that, you say, well, there's a line in between ingest and query. So while we had largely decoupled ingest and query, we've never done it quite 100%. And that's been kind of a distasteful part of the architecture for a while. So at the moment, we're working on a new version of our storage tier that can handle the live edge data, so we can actually push that problem into the storage layer and totally decouple ingest and query once and for all. As I said, we stopped shipping data around between cells. At the moment, we still have to move the metadata around, which still means we have the complexity of doing that transactionally and what have you. So this is also a thing where we are designing the next generation of our metadata system that will allow us to stop doing this sort of transfer back and forth. The thing here is that unlike while we could go back to using a very large S3 bucket or tier, we want to do this without running, once again, the largest installation of any particular database technology for the metadata. So that's sort of the problem to be solved here. And then we are looking at actually deploying multiple types of query cells for different types of workloads. So to kind of explain what motivates that, this is a chart that sort of represents a typical week of query workload at New Relic. So In the large, there's this sort of daily pattern that, this is sort of the normal day-to-day. People are looking at dashboards, they're running some simple queries, maybe they're handling an incident, what have you. But this is the sort of stuff that is generally looking at like the last hour or the last day. It's the stuff that people expect to be very fast. But it's also a workload that's like fairly easy for us to predict what it's going to look like. So we can scale up and down, but keep that hot storage tier available for this. What you can't do is very rapidly scale those tiers that actually have local storage. So there's this other type of workload that's these spikes that you see in the graph. And if we zoom in on one of those, these are actually like very singular events typically. So these are very isolated, massive increases in the query workload that we're seeing. So this is typically like someone who decides that they want to run a 3-month business analytics query. And that can be like 10 times as expensive as everything else that's running in the query tier at that time. It's also not going to be data that's actually in the hot cache on those disks. So we're going to be pulling this stuff out of S3 anyways. The queries are going to be slow. The customer is typically okay with that. They know the 3-month query isn't going to return in 50 milliseconds. So in order to handle this, we're deploying a different class of query cells that actually just do away with the disk entirely, purely stateless query workers that can be auto-scaled up and down very rapidly depending upon incoming query load. And then also, when Elon Musk gets to Mars and starts building data centers there, we're going to build some Galaxy Brain query routing to take care of that problem as well. All right, thank you for coming. I hope you enjoyed the rest of the conference.